to me. So yeah, so it's just a way of compaction, right? Like if you have a 32 bit number, so if you have a big number, let's say 1111110010101001, right? It's a pretty big number. So every time you will have to write that many digits. So instead of doing that, what we do is we can just break them into chunks of 4, and every chunk of 4 we can just write it in hexadecimal. So this 1111 is F, 1100 is 8 plus 4 is 12, so 12 is C, 4 plus 2 is 6, and 8 plus 1 is 9. So FC69 is now your hexadecimal. So you will see hexadecimal in a bunch of places. So when you if you do like some web programming, then your colors you will see are represented in hexadecimal, right? It will be something like so white is basically FF, which is basically saying you have FF red, FF green, and FF blue. So hexadecimal is just a way of compacting the binary number into a smaller number, so you can easily work with it. So you have seen this already actually. Like another kind of compaction you must have seen is when you set an IP address in your machine, the IP address looks like, for example, 10.194. So this is my IP right now, 158.117. So this is another kind of a compaction. So this is in 255 base, right? So each number can, sorry, 256 base. So each number can go up to 255, and so 256 is also 16 square is 256. So basically the same number here, if you were to write it in 255 base, what you can do is instead of creating chunks of 4, you can create chunks of 8. So this will be something dot something. So that is 255 base, 256 base. So basically this hexadecimal, this octal, they are more of a way of writing this large binary numbers in a compact form. Okay. So now we can, I think, get a little bit comfortable around addition and stuff like that. So any comments, questions so far? Like why do we need binary? Why do we study hexadecimal?
Sir, can you please once again explain that RCB one? Because my connection got interrupted. The RGB, the
Okay.
colors one.
Yeah, so every color is a mixture of some red, some green, and some blue, right? So it's just a, although this is not relevant to our codes or minors or anything, but to represent any arbitrary color in the computer, what you can do is, so what people have defined is a standard saying R can go from 0 to 255, G can go from 0 to 255, and B can go from 0 to 255. So by doing this, I can now represent any color, right? So basically what I'm saying is if all three are 255, then this is my white color. And so when I write all three in 255, it's basically FF, FF, FF in hexadecimal. And the representation is, it's written in a compact form like this with a hash FFFF.
How you're writing this FF and FF?
Okay, so yeah, so that brings us to how to convert a decimal to hexadecimal. Right, so basically 255, if you have to convert it to hexadecimal, you divide it by 16, and you will see that it's 15 is the quotient and 15 is the remainder. Let me, so 255 divided by 16, Yeah, 15 is the quotient and 15 is the remainder. Then if I do 15 divided by 16, I get 0 as quotient and 15 as remainder. And 15 is basically f, right? And then I write it in the reverse order. So it is ff. We can look at a few more examples. So to convert between decimal and hexadecimal, so let's say we are converting like 23, right? So 23, you can divide it by 16. You get 1 as a quotient and 7 as remainder. Then if I divide 1 by the quotient, 1 by 16, then I get 0 as quotient and 1 as remainder. And if I write it in reverse order, I get 0x17. So basically 0x17 and 16 is 23 in base 10. Right? And we can also do the other side conversion to verify. So 0x17 is what? 16 times 1 plus 7, that is 23. Right? So you must have seen this for binary as well. So if you want to convert 23 to binary, for example, you do, instead of 16, you divide it by 2 and you get 11 as remainder and 1 as remainder, 11 as quotient. 11 by 2 is 5, 1, 5 by 2 is 2, 1, 2 by 2 is 1, 0, and 1 by 2 is 0, 1, and I write it in reverse order. So it is 1, 0, 1, 1, 1 in base 2 is 23 in base 10. So if I write 1, 0, 1, 1, 1, just to verify, so this is.
So your screen is freezed. Yeah.
So it's basically 1 into 2 to the power 0 plus 1 into 2 to the power 1 plus 1 into 2 to the power 2 plus 0 into 2 to the power 3 plus 1 into 2 to the power 4. So this is 16 plus 4 plus 2 plus 1, which is 23 in base 10. So this is how you convert numbers from decimal to hexadecimal or decimal to binary. We can also do decimal to octal. So 23 divided by 8 is 2, 7. 2 divided by 8 is 0, 2. And if I write it in reverse, so it's basically 2, 7 in base 8 is 23 in base 10. Is this conversion clear? Like the process?
Oh, sir,
Yes,
I have one doubt, like not exactly related to this.
Uh-huh.
Like when you're writing a C code,
Uh-huh.
how do you hard code a number as an octal number? Like because like for hexadecimal you use 0x something, the 0x and you write the number. For
Yeah.
octal, what do you do?
I think it's 0O. So you write.
Sir, it's right that it's like some weird error is coming. Where like a 002 if I put,
It is
showing
just
it
an
as an
O.
error.
Just a 0, sorry.
Just a 0. Yeah. Then
It's just 0.
just
Wait,
yeah.
I'll try.
We can try it when we switch to laptop. So yeah.
Yeah, now it's coming. Thank you.
Okay. Cool. Cool. So yeah. I hope this is clear so far. So we can now try to get a bit comfortable with addition in different bases. Right. So let's say we are adding 23 and 39. So this is 9 plus 3 2. 2 plus 3 plus 1 is 6, right? So 62 in this is decimal. So 23 in binary is what? We just calculated it. 10111.
Sir,
Yeah.
will you also explain these conversion in programming also?
As in how to write a program to convert?
Yes, sir. How to convert 62 in binary or a number binary into decimal?
Uh, how about, so this is the process. I think now that you know loops, you should be able to write the program yourself. So basically the process is you divide it by that number, you come up with the quotient and remainder, then you take the quotient, then you again divide it by 16, and you keep doing it until your quotient is 0. And then all the remainders you just print in a reverse order. Yeah, so let's see, like if we have time, I can try to do it, but I was not planning to. I think you should be able to write this program now that you know loops. But we can try if there is enough time.
So
So to
can there,
print in reverse order, won't we need arrays? Because like the last number you're printing first, so first number you should store somewhere.
Yeah, that is a good point.
You can just reverse the number you get now.
We can multiply each time by 10 and add the next.
Yeah, so with arrays or with stack, it's much simpler. So when we learn stack, maybe I can show this, like how to do it with stack. It's actually will be much easier then. But for now, let's just try to remember the approach, like how to convert. So doing it in program is not too difficult. Like we will do it at some point. But for now, for this one, for today's session, let's just worry about how to convert between the two numbers. Like what is the process? Okay, so so I want you to get like a bit comfortable with switching between different bases. So that is the point right now. So let's just focus on that for now. Okay, so what is 39 in binary? Can anyone convert this?
32 plus 4 plus 2 plus 1.
So 32, then 60, there is no 16, there is no 8, 4, 2, and 1. Yeah. So this is 39. So if I add this, 1 plus 1 is 2. 2 is basically 1, 0 in binary. So 0 comes here, 1 goes there. 1, 1, 1 is 3. 3 is basically 1, 1 in binary. So 1, 1, 1 is 3. Then 1, 0, 0 is 1. Then 1, 0, 1, then 1. So it comes to this number, which is basically 32 plus 16 plus 8 plus 4 plus 2, which is 48, 56, 60, 62. Right? So we got the same number in, when we added the binary, we got the same number as the decimal addition, which is what we should have got. So then let's try to do it in octal as well. So 23 and 39 is 62. So what is 23 in octal? So we just did this, right? 23 in octal is 27. So we write 27. Then what is 39 in octal? So to convert 39, we basically divide it by 8. We get 4 as quotient, 7 as remainder. Then 4 divided by 8 is 6. Sorry. 0, 4. Then we write it in reverse. So it's 47. So now 7 plus 7 is 14. And 14 in binary is what? 1, 6, 0, 1. So 14 in, 14 in octal is 6, 1, 6 in, 14 in decimal is 1, 6 in octal. So you get 6 here, then 1 goes to carry. So 4 plus 2 plus 6 plus 1 is 7 in octal. So 76 in octal is basically what? 7 times 8 plus 6. 56 plus 6 is 62. So it works in octal. And let's just to flex our muscles a bit more, let's also do hexadecimal. So 23 plus 39 is 62. Let's convert 23 to this we had already done. So 23 in base 16 is 17. 23 in base 16 is 17 in base 16. 39 divided by 16 is 2, 7. 2 divided by 16 is 0, 2. Try to 10 reverse. So 39 in base 10 is 27, 27 in base 16. So this becomes an addition of 17 plus 27. So 7 plus 7 is 14, which is E in hexadecimal, and 1 plus 2 is 3. So this becomes 3E in base 16. Let's convert 3E back. So we get 3 times 16 plus E is 14. So we get 62. Okay, so let me know if I'm going very fast. So this is converting. We did the same addition in 4 different bases, and we got the same number every time. Any questions? Okay, no questions. So another thing we can do is let's take this output from binary, which is 111 111 right? This was my 62. So I can take uh, three. I can take chunks of 3. So 111 in a chunk of 3 is basically 7, and 110 is 6. So this should be my octal addition. This was my binary.
Sir, can we ask some questions about tomorrow's exam? Like,
After we cover this,
it's a very small question. Like, I just needed to ask if 3 theory questions will come. Any theory questions, like subjective type.
I think so. Yeah, actually, definitive answers can be received on Piazza. Like, I don't.
Okay, sir. Okay.
Yeah.
Okay,
Yeah. Okay. So yeah. So okay. So where were we? So 111, 110 in binary. If I take chunks of 4, so 1110 in a chunk of 4 is basically 14, which is E, and 11 is 3. So this is hexadecimal, right? Which is what we got here. Okay, so I hope you can add numbers in different bases now, and I hope you are convinced that you should get the same answer when you add in different bases, and hopefully you know how to convert between different bases. Okay, so let's move on to less than 1. So let's do the same exercise for 0.6. Yeah.
So, can we add the 3 numbers simultaneously in a binary?
Yeah.
So, like in that, if the power goes 4, so then we wrote 4 as 110, 100. So, in that case, what will be the that base and what will be the carry?
So the question is, if I add 3 numbers in binary,
Yes, sir.
right? Basically, we are adding, let's say, 111. So it's basically 4. Yeah, so in circuit, like this is not how it's done. Like you add two numbers at a time and then you add the third one.
Yeah, that's asking. So like we should like add two, then another one, then another one in a pair of two.
Yeah, it's the same thing. You will run into same problems. So if you try to add like 30 different numbers in decimal, right? Your carry can become really big. So it's the same. Yeah. So just to keep your carry between less than keep your carry less than two. Only
Okay. So also sir, like if for general question, like if I carry 4, then I write in a binary with a 100. So what will be the carry and what will be that base?
It's the same thing, right? Like when you do a decimal addition, if your
Yes.
carry is 23, what do you do?
Yes, sir, definitely it will go really big.
Yeah, the same thing. So you will take 3 in this position. Actually, what do you do in decimal? I think you just keep adding and the carry will keep going forward.
Yes, like carry will be like base will be a single digit or carry can be a more than one digit.
So generally, like the way it is implemented, carry is also only 0 and 1.
Okay.
Yeah. So that your carry is also a binary number. Otherwise, your carry.
Yes, sir.
Yeah. So think about this circuit, right? Like this is the basic circuit. So if you had to add, if A and B were more bits, then basically this carry will go back into the sum circuit. So that's how it works.
So will you again tell that sum of octal number?
Yeah. So for octal numbers, what we did was we converted 23 and 39 to octal. So to convert 23, what you do is you divide by 8. So you get 2 as a quotient and 7 as remainder. Then you take this quotient and then you divide 2 by 8 again. So 0 is quotient and 2 is remainder. Then you write it in reverse order. So you get 27 in base 8. Or 27 in base 8. Then we took 39. We took 39 and we did the same process to get 47 in base 8. So now 7 plus 7 is 14. But 14 is basically in decimal, right? So we need to express 14 back into octal. So 14 in octal, we follow the same process, is 16, 1, 6. So 7 plus 7 becomes 1, 6. So 6 comes here and 1 goes to carry. And then 1 plus 2 plus 4 is 7. So this is how we did the addition in octal. And indeed, 7, 6 is equal to 62.
Okay, sir.
Okay. So let's quickly do the same process for numbers smaller than 1. So 0.625 plus 0.75, so we get 5. 5 plus 2 is 7, 7 plus 6 is 3. 1.375, so this is decimal. So now we'll convert 0.625 into binary. So we keep multiplying by 2. So in this case, it becomes 1.3, uh, 1.25, right? 25. And then we take 0.25, multiply by 2, we get 0.5. We take 0.5, multiply by 2, we get 1. And then we write it in this order. So basically 0.625 in decimal is 0.101 in binary. So we took the first digits before the decimal. Similarly, 0.75 into 2 is 1.5. 0.5 into 2 is 1. Then we write it in this order. So 0.75 is 10 is 0.11 in base 2. So if I add them up, 0.101 plus 0.11, I get this can be 1 and 0. So 1 0 plus 1 is 1, 110, 1.011. And this is equal to 1 into 2 power 0 plus 0 into 2 power minus 1 plus 1 into 2 power minus 2 plus 1 into 2 power minus 3. This is 1 plus 0.25 plus 0.125, this is 1.375. Okay, is this clear?
No, sir. Can you repeat again?
Yes, sir. Repeat the pattern.
Okay, so which part is not clear? Is this part clear? Like how we converted from decimal to binary?
Sir, only decimal fractional number to binary. That's
This part. Okay. So it in previously when the number was bigger than 1, we were dividing by 10 every time, right? Sorry, dividing by 2. So like this was the process. We keep dividing by 2, and then we write it in reverse order. In this case, we keep multiplying by 2, and whatever digit we get before the decimal, we keep picking that up, and the rest of the digits after the decimal, 0.25, we take in the next iteration. So 0.625 multiplied by 2 is 1.25. So we take 0.25 and multiply by 2, so it's 0.5. Then we take 0.5 and multiply by 2, we get 1. So now that we have 1, we can just stop. So to write it, we look at the digit before the decimal to write it down. So it's 0.101. Similarly, for 0.75, we multiply by 2, we get 1.5. Then we take this 0.5 and multiply by 2, we get 1. And then we write it in this order. So we get 0.11. So is this, yeah, maybe this is looking like rocket science. Why are we doing this may not be clear. So yeah, we can, so is the process in mechanical form clear? We can try to understand why this process works next, but in the mechanical form, do you follow the process? So like what are you doing?
Well, sir, I have a small question here.
Yeah.
Yes.
So a very simple number in decimal like 0.1 or something can be a recurring decimal in binary, right?
Yeah.
So then in that case, how does it store those numbers then?
Yeah, let's get there after this. So we can, so the reason I chose these numbers are because they are not recurring. So they stop after some point, but we will get to your question after this. But first is, do you understand the mechanical process? Why this approach, like how this approach works? So we can look at why this works next. Okay, I'll assume.
Yes, sir. It was clear.
Okay, so I'll assume. Okay, cool. So let's look at why this approach works. So previously, we can start by looking at this one, which is we keep dividing and then we reverse. So why do we reverse and what is the meaning of all this? So basically, if you think about it, what we are trying to do is we are trying to express 23 as, let's say, x0 plus 2 times x1 plus 4 times x2 plus 8 times x3 plus 16 times x4, right? So this is a equation we are trying to solve, and we don't know the values. So we are trying to find the values of x0, x1, x2, x3, and x4, right? So basically, if you look at this expression, everything here is divisible by 2, right? So if this number is odd, then you know that x0 is equal to 1, right? If this number is even, then x0 should be equal to 0. So from this you know that x0 is 1, which is same as saying it's the remainder of 23 when divided by 2. And now we can follow this process recursively. So if I divide it to this, yeah. So I can write it as 22 plus 1, 60. Right. So now what I can say is 11 is equal to 8x4 plus 4x3 plus 2x2 plus x1. Right. So now you know that x1 is equal to 1 because this number is also odd. So next I can write this as 10 plus 1 is equal to this whole thing here plus 1. And then 1 and 1 is gone, so divide the whole thing by 2 again. So 5 is 4x4 plus 2x3 plus x2. Right? So basically, by doing that process of finding the remainder and finding the quotient, we are recursively solving this equation. So we can look at it again. So here, like since 23, when you divided it by 2, the remainder was 1, we concluded that x0 is 1. So this is same as saying if I go reverse in this direction, basically the first least significant bit is 1. So we found this bit. And then when we do it again, we found this bit. And then when we do it again, we find this bit, then this bit, and then this bit. So this is the intuition for why we keep dividing by 2, getting the remainder, and then do the reverse. Which is basically because we are trying to solve this process. Okay, does this make sense? I hope, yeah, I'll take that as a yes. So we can look at with the numbers less than 1. So what we are trying to do for 0.75 is we are trying to say 2 power minus 1 x1 plus 2 power minus 2 x2 plus 2 power minus 3 x3 and so on, right? So we are trying to solve this equation given 0.75. So what we will do is, so we know all of these numbers are currently less than 1, right? So even if everything is 1, this should be less than 1. Is that true?
Yes, sir.
Yeah, okay.
Yes, sir, cos x1 and x2 all can be 0 or 1.
Yeah, okay. So if I multiply this by 2, I get 1.5 and then I get x1 plus 2 to the power minus 1 x2 plus so on. So this whole thing is still less than 1, right? So we know 1 is x1. So we are left with 0.5 is 2 to the power minus 1 x2 and so on. And if I multiply it with 2, I get x2 plus 2 to the power minus 1 x3 and so on. And since all of this is less than 1, I know x2 is equal to 1 and x1 here was equal to 1. And so we are left with 0 is equal to 2 to the power minus 1 x3 and so on. So we conclude all the x3, x4, they're all 0. So again, this is the process we are following here, right? We keep multiplying by 2. We look at the first digit. We look at what is before the decimal, and then we take the rest of the number, then multiply by 2, then we take rest of the number, multiply by 2, and so on. So again, the rationale is only one of these values can be, so that everything else is less than 1. Yeah.
Sir, you have taken off 0.75 decimal number. If there is the 0.85,
Yeah. So yeah, so in this case, like it basically ended at some point, right? But like you rightly pointed out, it may not end. So if I have 0.85, right? So I multiply this by 2, I get 1.7, right? So then I take 0.7, I multiply by 2, I get 0.4. I get 0.4, I multiply by 2, I get 0.8. Take 0.8, multiply by 2, I get 1.6. 0.6 is 1.2. 0.2 is 0.4. And now we are repeating again, right? So it will never stop. So this is basically 0. Just going downwards. So 1, 0, 0, 1, 1, 0. And then we repeat from here. So it will be 0, 0, 1, 1, 0, 0, 1, 1, and so on. So this number never stops. So yeah, it's a infinite, it's a repetitive thing. The pattern repeats after some point. Okay, any questions? We can switch to laptop after this if there are no questions. Oh yeah, we can try to do this for octal as well, just addition bit. So basically we were doing 0.625 plus 0.75. This was 1.375. I'll just try to do it in octal as well. So I multiply this by 8, and 0.625 times 8 is 0.5. So I get, and then 0.5, no, sorry. 0.625 times 8 is 5. So basically 0.625 in decimal is 0.5 in octal. Is this right? Yeah. So then 0.75 times 8 is, I think, 6. So 0.75 in decimal is 0.6 in octal. So our summation problem becomes 0.5 plus 0.6. 6 plus 5 is 11 in decimal, which is basically 1.3 in binary, in octal. So this addition becomes 1.3. So 1.3 in octal is 1.375. Oh, sorry. That is what we want to prove. So 1.3 in octal is 1 times 8 plus 0.3 times 8 power minus 1. So this is 1 plus 0.3 times 0.125, which is 1.375 in decimal.
Shouldn't it be 3 times 0.125?
Oh yeah.
So shouldn't it be 1.1, 0.5 plus 0.6?
Yeah, so 5 plus 6 is 11, right? But that is 11 in decimal. So we want to express 11 in octal. So 11 in octal is 1.3. So that's why we write 1.3. So remember, this is an octal addition. This is not a decimal addition. So you have to make sure that your addition is written in octal. Right? So similar to when you add 1 and 1, you don't write 2, right? You write 1 0, which is basically 2 in binary. So when you add 1 1, you don't write 2, you add 1 0. So similarly, when you add 5 and 6, you will not write 11, you will write 1 3, because this is an octal addition.
Yes, okay.
Okay, great. Perfect. So let's move on to the laptop. So we'll just switch over. We'll try to convert 0.2 from decimal to binary and then switch to laptop. So 0.2 is, just go over quickly, 0.4, this is 0.8, 0.8 times 2 is 1.6, 0.6 times 2 is 1.2, 0.2 times 2 is 0.4. So now we are repeating again. So this number becomes 0.0011, and then repeating again. So 0011, 0011, 0011, and so on. Right. So if we write 0.2 in float, right? So this is just a simple conversion. So now the next is how is this kept in the laptop? So basically, it's you can write it as 1.1001. So shifted by 3 decimal points. And multiplied as 2 power minus 3, right? So because I shifted it by 3 decimal points, I will write it as multiplied by 2 power minus 3. So now, if you remember, in our float representation, we had 1 bit as the sign bit. Then we had mantissa, and then we had exponent. This is M, this is E, this is S, and your number is minus 1 power S multiplied by 1 plus 0 point mantissa multiplied by 2 power E minus 127. So now basically what is our mantissa? Our mantissa becomes this number, which is 1001, 1001, 1001, and so on. And then our E becomes, so E minus 127 is minus 3. So E becomes 124, which is same as 64. What is 124 in binary? 64, 60, 32. Okay, I can just Google it. It's
Sir, can you repeat again from my throat sign mantissa?
sorry.
Can you repeat again?
Which part? This part?
From float, sir.
Huh?
You write it float, sign mantissa, and exponent. From there.
Okay. So hopefully this conversion is clear, right? So we converted 0.2 into decimal, and then we converted into what is called the scientific notation, which is 1 point something multiplied by 2 raised to power something. So we shifted it by 3 decimal points, and we wrote 1.1001, 1001, and multiplied it by 2 to the power minus 3. So in our float representation, the way it is represented is the first bit is sign bit, then the next I think it's 23 bits, right? Is it? Yeah, the next 23 bits are Mantissa. Wait, am I mixing things up? Sorry, let me take a look. Yeah, I did mix things up. So yeah, the 31st bit is sign bit, then 30 to 23 is exponent, and then 22 to 0 is Mantissa. Yeah. This is
Why you 2 to the power of -3?
Why did we do 2 to the power -3?
Yeah.
Yeah, so you know, in decimal, when you have to write, let's say 0.015, when you convert it into scientific notation, you do 1.5 into 10 to the power -2, right? Because we are shifting this by 2 decimal points, by two digits. So it's the same concept here. So 10 was our base, right? So from the same concept, we are shifting it by 3 points, 3 digits. So 1, 2, 3. So that's why we write 2 to the power -3.
Sir, if there might be 0, 1, 1, 1, then you have to shift it by only one digit.
Say that again. Yeah.
Sir, if there might have been 0, 1, 1, 1, then by how much digits we have to shift?
Where is the decimal?
In front of 0.
Okay, so then you will shift it by 2 points. So it will be 1.11 into 2 to the power -2. So the point is you just want to get a 1 here.
Okay. Okay, sir. Means there should not be 0.
Yeah, you don't want a 0 initially, you want a 1.
Okay, sir. Okay.
Okay, so let's switch to the laptop. Okay, share my screen. Okay, can you see my screen?
Yes, sir.
Yes.
So this is the program that I think it was showed in the class, which is we will print how the float looks like in the binary format. So here I'm printing 0.2. So if I run this, and I print 0.2, this is what I get. So the sign bit is 0 because this is a positive number. Then the exponent is 11110, which is 1 times 64 plus 1 times 32 plus 1 times 16 plus 1 times 8, 1 times 4. So this is 8 plus 4, 12, 28. 28 plus 32 is 60 plus 64, 124. So which is E minus 127, right? So what did we have here? Yeah, so E right, so E minus, so this is E basically, so E minus 127, so this is my E, and E minus 127 is -3, which is what we wanted. And then for Mantissa, this is the Mantissa. So it's same as the repeating pattern 1001, 1001, 1001, as we saw when we computed this. Cool. So there was a question basically. Basically, we won't be able to keep. So since we have limited number of bits, right? We won't be able to keep infinite number of bits for 0.2, even though 0.2 needs the infinite number of bits. So let's see what happens because of that. So here I have a float which is 0.2, and I just want to print it back. So if I run this program, I see that actually because of this precision problem, like I was not able to keep infinite number of bits. So because of that, the value is actually a little bit different. So this can have implication in your programs. So let's see. Okay, so here is a program, right? Like, so this is basically just looping from 0 to 20 with increments of 2 in an integer operation. And it is counting how many times I'm looping through the loop. And then it is doing the same thing by dividing this 20 by 10 and this 2 by 10. So it's 2.0 and 0.2. And instead of int, we have float. So it is doing the same thing. Just the difference is intuitively it is doing the same thing. So the difference is here it is int, here it is float. And the numbers are divided by 10. So what do you think will be printed in this case for the count? Hello. Um,
11. So
11.
in the upper part, it is 0, 2, 4.
Yeah, 0 to 4 all the way to 20, right? So it should
All
print
the even to 20.
yeah,
So 11.
11, right? And then here as well, it should print 11, right? Because it is technically the same program. So
But it will not. So.
Yeah. Otherwise, I wouldn't be showing. So as we can see, in this case, it is printing 11. But in this case, it's actually only printing 10 because of the precision problem. So here, since it is a little slightly greater than 0.2, so the loop actually ends after just 10 iterations instead of going to the 11th iteration. Since the next time you add 0.2 into this, it is already greater than 2.0. So yeah, like just by knowing this, how the float is stored, you can avoid such problems, and you can try to basically avoid confusion. If you see something like this, you know what is going on.
So when it comes to 1, it prints the exact correct value. Like at also 2, it prints the very correct value.
Yeah. So one. Um, yeah, let's try this. So yeah, that is a good observation. Yeah, 1 is accurate in float, right? So 1 doesn't have infinite number of bits. When you have to express 1. So actually, let's do something. Let's print it in the bit format. So you have not studied functions yet, so don't worry about what I'm doing here. But let's just see it in the let's see. Let's see if this works. So don't worry about what I did in the program, but basically along with printing the number, we are also printing it in the float representation. So as we can see in 0.000, this is accurate because there is no loss of precision. In 0.2, there is already loss of precision. What happens in 1? So when you are 1, your mantissa is exactly 0. So this makes sense. And your exponent is 127 minus, what is this, 127 minus 127. Yeah, so exponent is 1. Yeah, so that's why there is no loss of precision. So yeah, this 1 is accurate because there is no, in the decimal bits there is no loss here. But again, when it goes to 1.2, it is again there's loss.
So like when it adds 0.2 to the 0.8 thing, how does it exactly become 1?
That is a good question. Yeah, so I'll have to. So I think it will be doing a bit addition on this, bitwise addition on this. So since the exponent is the actually on, so we can try to add this. I'm not sure, but let's try it. So let's try to. So we are adding 0.8 with 0.2. So let's do the bitwise addition. What do we get? We get 0 here, carry of 1. Then we get 0 here, carry of 1. This is already.
So why the number is always greater, like shouldn't it be less, like we are losing some precision?
Why the number is greater? So I think the number is greater because it seems there is some rounding off going on. So this should have been 1001, 1001. Finally, it should have ended at 100, but it seems like it did some rounding off to get 101. So that's why it's greater now. But you are right, if this was 0 and the rest of the things were chopped off, then this number should have been less than 0.2. But because of this 1, I think that's why it's greater. Yeah, so this is a good question, like why. I'll have to look at the addition. Adding this with this gives exact 1. It doesn't look like it should. So the exponents are the same. So we don't have to worry about exponents. Oh, exponents are not same. Okay. Oh, exponents are not same. Okay, my bad. Okay. Yeah, I'll have to look at the float addition, exactly how it works. So then I can answer. I don't know right now. But if the exponents were the same, we could have just added the mantissa, which is what I was trying to do. But exponents are different. So I think something will get shifted and then added. So yeah, I don't have an answer
So
to
in
that.
float means by default it gets printed it up till 6 decimal only, no?
Yeah.
So here up till 6 decimal they are accurate only. So I think maybe that is the reason.
No. So internally it is stored like this. So it doesn't matter how you're printing it. So internally it is this number. So we are printing it directly using the bit mask thing. So internally it is this number. So even though top 6 digits are maybe accurate, but this is not equal to 0.2. So when you do addition, you will see problems. Okay. Yeah. Cool. Yeah, I'll have to get back to you on this addition thing. Why is 0.8 plus 0.2 exactly 1.00? So basically we need to understand how the float addition is working. Basically how they are modifying this exponent, modifying the mantissa according to the exponent and then doing the addition. Cool. Okay. So let's see. So we are done with the looping. Yeah, rest are more advanced things, so we can look at some interesting things. But any questions so far, like converting between bases and seeing the loss of precision in float? Like doing addition in different bases, converting
The
between
exponential part which is used, you have mantissa part and it's.
Sorry?
So you have used the mantissa in decimal number, you have used mantissa, exponential. Will you repeat that part?
Okay, sure. Sure. Let me print this. So GCC print float. If I run this, so basically 0.2 is this. Let's remember this. Okay, I posted in chat. So we will remember 0.2 is basically this. So let me switch to the iPad again.
So it's end, or we have assumed that the number has ended. It is non-ending number, I guess.
Yeah, but your memory inside your laptop is not. You cannot just use infinite memory to store 0.2, right?
Okay.
So that's why you only want to use 32 bits. And that's why you lose precision. To have a very, very accurate 0.2, you actually need infinite number of bits.
Yes.
Right? But float is 32 bits, so that's why you lose precision. So let's look at this, how we got this number. So basically, when we converted 0.2 from decimal to binary, we got 0.4. So I hope this process was clear. So we keep multiplying by 0.2 and then we pick the number before the decimal and then we write it in this order.
Yes,
So
sir,
that,
this part is clear.
yeah.
Up to this.
Okay. So we took this, converted into scientific form by moving it 3 decimals. So we got 2 to the power minus 3. and then 1 point da da da. So your mantissa should be, so when you write a float, it is sine, then exponent, and then 22 bits of mantissa. So you should see sine is 0, right, because it is a positive number. Your mantissa should be 1001, 1001, 1001, and so on. And your exponent is e minus 127 is minus 3. So you should see e as 124, which is 0, 1, 0, 1, 1, 1, 1, 1, 1, 0. So now go to the chat and look at the number that was actually printed. So the first bit is 0, which is the sign bit. Then you get 0, 1, 1, 1, 1, 0, 0, which is the exponent, this one. And then you have a repetition of 1001, 1001, 1001, and so on, which is your mantissa.
It is written in which form? The final answer you have given?
This is the bit representation of float. So when you have 0.2 as a float, this is how the computer is actually storing it.
And what it does not store in the value that you have written above. It is 0.001, 1001.
This one.
This.
So this value is the same as this value, right?
Okay.
So I just moved the decimal point, right? Actually, yeah. So it's minus 1 power s, 1 plus 0.n, 2 to the power e minus 127. So basically, float stores is like this. These are the 32 bits, right? So first bit is the sign bit, next bits are exponent, and then next 22 are mantissa, 23. And it is interpreted as this. So it is interpreted as minus 1 power s, 1 plus 0 point mantissa, 2 power this. So we convert this into, so we want to put this into this form. So what do? We see that first of all s is 0 because it's a positive number. Then we see m is everything after the decimal. So that's why m is 1001, 1001, and so on. Next we see e minus 127 is minus 3. So our e becomes 124. And which is 124 in binary is 0111 1100. So that's why when you come here, you see s, the first bit is 0. Then the next 8 bits are exponents, so 0111 1100. And then it is mantissa, so 1001 1001 and so on.
Sir, in the mantissa, why is the last part 101? Like, has it been rounded off?
Yeah, it seems like it is rounded off. So that's why yeah, so this is rounded off. So that's why when we were printing it back, it was, the number was greater than 0.2. Okay, so there are some questions. So 23 base 10% O. Will we get subjective type questions? How come 13 is E? Oh, did I make a mistake? Okay, someone corrected it. So 13 is D in hex. Okay. C analogous to decimal will be easy to understand. If we see it as analogous to decimal, I don't know if that is a question. When we would start array. So this is a lecture. I think in next 1 or 2 weeks we should study arrays. How much would be stored in exponent part for double, as it is 64 bit? Okay, so we can look at this one. I don't remember it on top of my head, but we can look at it. So double representation in C. This is, yeah, not. Yeah, how about, yeah, I can post it in chat how the double is represented after this session. Concept of two complements for float. So no, there is no concept of two complements for float because we already got the sign bit. So we are already able to express the negative numbers because we have the sign bit here. Why is e minus 127 minus 3? I did not understand that. Yeah. So basically, when a number is written like this, it is interpreted in this form, right? So this is how the computer is interpreting it. So what we want to do is we want to make this equal to this, equal to the representation of 0.2, right? Because we want to represent 0.2. So that's why we got sign bit as 0 because there is no negative 1. We got Mantissa as this number, everything after decimal. And we got e minus 127 as minus 3. So it's just how the computer interprets this 32 bits as a float. So since it interprets it like this, we equal this with the representation of 0.2, and that's why we equate e minus 127 with minus 3. Sir, in general, can we expect the float to be greater due to rounding off? So actually, you can try it on your machine as well. I don't think it happens. I don't think it is guaranteed actually, but you can try it on your machine as well to print 0.2 if you get a greater number. This sign representation is representation of float. Can we also use this to represent? Okay, this is not complete question. Okay. Okay, I'll just quickly show one other thing and then we can stop. Let me stop sharing here. Start sharing here. Okay, can you see my screen?
Yes.
Yeah. Yes. So basically, I just want to show you like 2's complement is actually pretty awesome. I just want to convince you of that. So this is a simple program which is taking an integer number and then it is printing it in unsigned form and signed form. So let's run this. If I run this, I get unsigned number as this and the signed number as this. So this is fine. Now if I take the same program, so the difference is basically here it was a signed number, int a is equal -1, and then here it is unsigned number, which is we don't have time to look at it, but basically it's the 2's complement representation of -1. So when I run this program, I get the same output, right? So in this one, it is interpreting -1 as an unsigned integer. So that's why it was printing this. And here it is interpreting this unsigned number as an integer. So it is printing -1. So we can actually do -s to look at the what is called the assembly program of these two things. So when you do dash s, it basically produces a file called unsigned.s for unsigned.c, and for in.c it produces in.s, right? So although the programs were different, right? So let's look at the programs again. So in one program we had, so this is vimdiff, by the way. This is showing you the difference between the two files. So it is showing that these two lines are the same and these lines are different. So in one program we had an integer, in another program we had an unsigned int, and it differs here as well. We have actually, let me just change it to a. Yeah, so the only difference between the two programs is this is a unsigned int, this is a int, right? The rest of the program is the same. So if I, but interestingly, if you look at the if you look at the assembly output of the two programs, so again I'm running vimdiff. So this is showing that actually the assembly program is exactly the same. So even though in your program we will not worry about what is here, but this is just trying to convince you that the assembly program for unsigned int and integer is exactly the same. So this unsigned integer and integer are just like a C construct. Your computer doesn't care, so it just wants to do integer operations on 32 bits. And this is achieved in this program. So similarly, if we try to do a float, if we change this to float, right? So again, these two programs, one is integer, one is float. In these two programs, if I want to look at, so now let's compare float with the integer assembly. So it is showing that the assembly are actually different, because the representation of float is actually very different from the representation of integer. So it cannot generate the same assembly for the two data types. So this was just something I wanted to show, like a interesting tidbit about like some of the constructs you see in language can just be a language construct. Your computer need not know what everything means. But yeah, this is not covered in the exam, so anything, just small. Yeah. Okay, so that is all I had. There's one more comment. So this representation is representation of floats. Can we also use this to represent ints? So you could say float x equal to 2, and that is fine. But remember, like everything, so you need to have different circuits for floating point operations and integer operations, because the way you add integers is different than the way you add float, and so on. And operating on floats is generally more expensive than operating on integers. So if you have only integer, it's better to store it as integer, because the program is likely to run faster.
Sir, I have a doubt.
Yeah.
Sir, in the class we had a program where we had to, where sir took in two numbers with signs, and we had to output the plus or minus whatever the answer is using 2's complement. Sir, here suppose we are taking in -2, so if the sign is negative, then sir did one line that x odd equal to with 0, x, 8 and 6 zeros. So sir said that this was to make the first digit 1. But why was it necessary? When we are doing 2's complement, that is, we are inverting the bits and adding 1, then always won't we have the first digit 1?
So first of all, by doing a OR, you are not hurting it, right? So even though it is 1, if you do a OR, it will be 1. So the next question is, if I can remove the OR, is what you're proposing. So you are saying the first bit is anyways 1. It may not be true, right? So if I have 4 and if I invert it, yeah, I think I can't think of a case where it may not be true, but just by doing the OR, you are not hurting it.
So like suppose we had an overflow, then how would it help making the first digit as 1? Maybe in case of, like if you had a carry 1 over and so it becomes all 0, so that's an overflow. But how would it help making the first digit 1, even if it's an overflow?
It is not supposed to help with the overflow. So this is just how it is represented. So you only have 32 bits, right? So you want to use the same 32 bits to represent both positive and negative numbers. So it's just a way of fitting both positive and negative numbers in those 32 bits. It's not supposed to help with overflow or anything.
Okay, sir.
Okay, cool. There's another question in chat. Representing 0, representing infinity, representing not a number. And then the comment is, how is the first representation 0? Is it because of rounding, because of extra bits? Yeah, so I think this was discussed. So basically this is close to 2 to the power minus 127, right? So that's why we just assume it is 0. So in your scientific notation, there is no other way to represent 0 because you want to do 1 point mantissa. So what you did is, by making your exponent to 0, since it's 2 to the power e minus 127, so by doing 0, 0, 0, your exponent becomes very, very small. So that's why it approximates 2 to the power minus 127 as 0.
So can you explain why we do e minus 127?
Just so you can have both positive and like both large and small numbers. So you want to, so first of all, you don't, so by doing that, if your exponent is less than 127, you are able to represent very, very small numbers, right? And if your exponent is, so another option was, we could say, I will just write it as 2 to the power e instead of 2 to the power e minus 127. So by doing that, it is now hard to represent. So now you have to worry about how do I make this exponent negative. So now you have to again do 2's complement and stuff like that in the exponent, which becomes more complicated. So this is a simpler notation. So you can store both large numbers and you can store small numbers without worrying about making exponent negative.
So like exponent has from 30 to 23, so it has 8 bits, right? So like how are we like sort of representing it?
What do you mean?
Like why 8 bits only?
This is just a choice. I mean, so in double, like I can send the double one later, but in double, I think there are more exponent bits. and then also more Mantissa bits. So in some languages like MATLAB, I think you can adjust this, but this is just how C is doing it. So yeah, I think you could, in theory, build another computer which uses 10 bits for exponent, but it's just a standard now. So yeah, there is no real reason behind it, I think. Okay, so if there are no other questions, we can stop here. I hope this was useful. And yeah, best of luck with your minors. I will get back to you around the 0.8 plus 0.2 question, how that is 1.00. Cool. Thanks everyone. Take care.
Thank you, sir.
Yeah. Bye.
Thank you, sir.
Okay, sir.